Good morning, everyone. So this is going to be the last lesson of Unit 4. And in this lesson, we are going to be talking about acid and base reactions. And so this is, it's actually a bit of a review. We covered acid-base reactions in Unit 2. When we talked about reactions in general, and acid-base reactions are a type of double displacement reaction, but we're just going to kind of go into a little bit more of what's happening with the actual ions, and maybe just to understand, kind of what is happening within the solution itself. So again, we're just going to expand a little bit on what we did in Unit 2. All right, so whenever an acid and a base combine, it's called a neutralization reaction. And so a neutralization reaction follows a very typical pattern, and that pattern is it produces a salt plus water. Now, again, we now know that a salt doesn't necessarily just mean NaCl. A salt could be really any ionic compound is a salt. So just be aware of that when we say ionic compound, we mean a salt, but there are many different salts. For instance, down below I show here sodium nitrate is a type of salt. And there are hundreds of different salts that are out there. So just be aware that it's not just NaCl. So this is kind of what we saw in Unit 2, an acid plus a base. And remember that an acid is a compound that starts with a hydrogen, and a base is a compound that has a hydroxide. And so an acid and a base will basically, the cation from the base, which is sodium in this case, will join with the anion, which is the negative ion from the acid. Those will join and form the salt, and then the hydroxide and the hydrogen ion will then join and form H2O. And so that's kind of the double displacement part of this reaction. Okay, so I want to just look at it from what's happening from an ion perspective. And I've got a little applet that I'm going to use. And so I'm just going to go over that exact same reaction. So it's nitric acid, HNO3, and sodium hydroxide. So as we've seen, is that the resulting reaction is H2O. It forms H2O and NaNO3. But let's look at it from an ion perspective. Now, if you had the nitric acid, the fact that it shows that it's aqueous here means that it dissolves in water. And sure enough, as a total ionic equation, we would then break it apart, and we'd write it as H plus aqueous plus NO3 aqueous. And if I were to put those into a beaker, sure enough, it would just look like a glass of water, a beaker of water. You wouldn't see those ions because they dissolve. I want to just clarify one thing, and this is based on our theory lesson last day, is that H plus doesn't exist for very long in water. It quickly joins with a water molecule, and it becomes something called hydronium, and it becomes H3O plus. So just be aware that anytime you see H plus, really what you're seeing is H3O plus. It's the same thing. It just means that the H plus has joined with a water molecule to form H3O. Okay, so here it is. In ion form, you've got all these H plus and NO3s that have broken apart and become ions. Well, in the same way, in another beaker, we've got sodium and hydroxide, and because it's aqueous, they have broken apart into their sodium ions and their hydroxide ions. And so again, it would just look like a glass of water. Unless you had seen me put in the sodium hydroxide, you couldn't tell the difference. This is what we've got to begin with. Now, obviously, if you had litmus paper, you could put a stick of litmus paper in, and in the base, the litmus paper would turn blue, and so you'd know the base was there. And in the acid, you could put the litmus paper in, and it would turn bright red or pink, and that would show you that it's an acid. So you could tell the difference between these, but certainly just from a visual standpoint, they just look like two glasses of water. Okay, well now what I'm going to do is I'm going to start pouring them together, and you're going to get a reaction occurring. Okay, so what's this reaction that's going to occur? Well, here I'm going to show you a little demonstration of what's happening here. So in this picture, I think it's good to visualize what's happening. And so I just want to emphasize a few things. So first of all, these pink molecules with the little gray attached to them, those are water molecules. And so you can see that they're the background of this entire reaction. So they dominate, that you can see them everywhere. But in amongst these water molecules, we have these other ions. And so you can see we've got sodium ions, and they're represented by this yellow plus circle or sphere. We've got hydroxide ions, which are a red with a negative and a little gray one. So those are hydroxides. We've got nitrate ions, which are the NO3s, a negative ion. And then finally, we have this hydronium ion. And remember, so I want you guys to understand that it's really a hydrogen ion, but it's quickly joined with the water. So this is what's happening as I pour these together. So I want you to picture in your mind that we have now poured them together. We've got a lot more liquid now. And within those, then, we have all of these ions present. All of these ions are floating around, okay? And remember, the only difference between my little animation is that it'll be as it's showing the H plus as an H3O plus, which is just the H plus joined with a water. Okay, so you got all these ions floating around in there, and let's see. So you can see them all moving around, and you know the water molecules are moving in the background as this happens. Now, if you have two of the same charged ions, two negative ions collide, nothing happens. They repel each other. So look at this. If you have a hydroxide ion run into a nitrate ion, they're both negative, they're going to repel each other and they push each other away. So kind of keep your eye on those. They repel one another. Okay, but not only that, but so when sodium ions collide with the nitrate ions, again, nothing happens with those. That's, you know, they're soluble, and so they're not going to collide. They're not going to combine at all. When the sodium ions combine with the hydroxide, nothing's going to happen. And when the H3O combine or run into an NO3, nothing happens. So there's all these mutual repulsions that are happening. So if those things are happening, nothing, you know, they don't stick together for a long period of time. However, here it is. When a hydronium ion combines with a hydroxide, when they meet, you've got a reaction that occurs. And basically what happens is you've got a transfer of there's an electron transfer between these. So watch this. As they combine, they're going to hit, and you get this transfer occurring, okay? And two water molecules are forming, okay? So essentially this transfer means that you've got this reaction occurring. So you've actually got a rearrangement of the atoms, and that's the definition of a chemical reaction. And so that this transfer occurs. And so in here every so often you'll get a transfer occurring, and that's the reaction that's happening. Okay, so let me go back here. So every so often you will get a hydroxide and a hydronium combining. Okay, so they will hit, and the resulting reaction will produce two H2O molecules. It'll produce two H2Os. So let me just show you here in our total ionic is that in this case, you've got an H2O. Now the Na and the NO3, nothing happens with them. They remain as spectators. So look at this. The Na and the NO3 don't change. They're spectator ions. And you've got the H plus and the OH combining to make the H2O. The only thing to remember is that, in fact, really, it's an H3O plus an OH minus, and then technically they actually make two H2Os. Either one of those is fine. When you look at those, like I'm fine with you thinking about it as H plus or H3O, and it'll either be one or two H2Os that are being created. Okay, so that's the total ionic equation that's happening here. So from an ion perspective. Okay, well, let's look at some of your homework questions. So this is a typical homework question, and it's showing, it's now getting into quantitatively what's happening. So we're going to use actual concentrations, and basically we're going to use stoichiometry. So we're going to use our steps of stoichiometry to solve an acid-base reaction. So the question here is, what volume of a 0.5 mole per liter solution of sulfuric acid is required to neutralize 56.5 milliliters of a 0.1 mole per liter solution of ammonium hydroxide? Now, I want to highlight something here before we start into this question, is that a lot of you may look at this question and say, oh, this is looking like a C1V1, C2V2 question, like a dilution question. And the reason you may say that is that you've been given a one concentration, a volume, and another concentration, and you may say, oh, this is going to be that quick one that I can do, the dilution. The key thing I want to emphasize here is, so it's not a dilution. The reason being is that there's a reaction that's taking place, and you've got two different substances. In one case, you've got sulfuric acid. In the other case, you've got ammonium hydroxide. So here, and it says the word neutralize. So you know that a chemical reaction is occurring. So it's not just that you're taking sulfuric acid and diluting it to another concentration of sulfuric acid. You're actually reacting them. So just be aware, a lot of students will read a question like this and will think that they can use the dilution formula. Now, interestingly enough, the dilution formula will sometimes give you the right answer, but only when the reaction is a one-to-one reaction. So even though you may get to the right answer, it's not correct. You need to use your steps of stoichiometry to solve this. Okay, so here we go. I'm just going to undo all that just so that it's not left on my note and people are confused who didn't watch my video. Okay, there we go. Okay, so step number one of stoichiometry is a balanced chemical equation. Here we go. So it says sulfuric acid, which I know is H2SO4, and it's a solution, so I know it's aqueous, plus ammonium hydroxide is NH4OH, and I know that that's a +1 ion and a -1 ion. So I don't need any subscripts. There's ammonium and hydroxide, and again, it's aqueous. Okay, and I recognize that this one is an acid. Well, it tells me it's an acid, and I know that ammonium hydroxide must be a base because there's the hydroxide. Okay, so I know that it's going to make a salt and water. Remember that the cation for the salt comes from the base, and the anion for the salt comes from the acid. So I just stick those two together. I go NH4 SO4, so it's ammonium sulfate. Now, ammonium is +1, sulfate is -2, so I'm going to need a 2 there. Remember, you've got to use your charges to write the correct equation. So it makes ammonium sulfate plus water, okay, the OH and the H. So now I've got to balance my equation. And so I look at this and I say, well, I'm going to need a 2 there to balance the ammoniums. And then I quickly look here and I know I'm going to need 2 waters because I'm just focusing in on my OH and my H2, and I see that there are 4 H's there, so I need the 4 H's there. Okay, so basically I make liquid water and I make aqueous ammonium sulfate. There it is. There's your balanced chemical equation. Let's write down what we're given. It says what volume of a 0.5 mole per liter. So look at this. We've got a concentration here of 0.5 moles per liter. And I'm just going to put here the volume is the question mark, is required to neutralize. Well, here we've got a concentration of 0.10 moles per liter, and a volume here is 56.5 milliliters. Now, I want to just emphasize one thing here. It says what is required to neutralize. And so in a neutralization reaction, you know that you're neutralized when you have stoichiometrically equal amounts. In other words, when you've got the same amount of acid and base present stoichiometrically. And the reason why I'm saying that, the word stoichiometrically, is that that's going to account for the fact that twice as much of the ammonium hydroxide is required. So you're still going to follow stoichiometry here, but I'm just trying to emphasize here that the word neutralization means that you've essentially got you've got the same amounts of acid and base to make sure that they completely cancel each other out. Okay, so ladies and gentlemen, step number 1 of stoichiometry is done. We've balanced our chemical equation and we've written down what we've been given. Okay, here we go. Step 2 of stoichiometry, and I'm going to write it over here, and you'll see why, is that step 2 is to convert to moles. Well, notice that the only thing that we've got enough information to convert to moles here is the ammonium hydroxide. I can't convert the sulfuric acid to moles because I don't know what volume I have. So the only one that I can convert to moles is this one. And I can say, well, N is equal to C times V. It's one of my hub formulas for converting to moles. If I have the concentration and the volume, I multiply them together. I do have to convert this one to liters, so I divide by 1,000, and you get 0.0565 liters. So here we go. My number of moles is going to be 0.1 times 0.0565. That's going to convert that one to a count. And multiplying by 0.1 just means shifting the decimal place another one. So it's 0.00565 moles. Okay, so I've now done step number 2 of stoichiometry, which is I've converted to moles. Okay, step number 3 of stoichiometry is to do a mole ratio. These are just our 4 steps. I didn't have to do the limiting reactant step because I wasn't given two amounts. I only have the one amount. So I don't have to do that little extra step for calculating the limiting reactant. So step number 3. So watch this. I've been given something about the ammonium hydroxide, and I need to calculate something, which is the volume of the sulfuric acid. So those are the two ones I'm interested in. I'm not interested in the salt or the water. I'm not interested in the products. I'm only interested in the reactants in this one. So I set up my ratio, and I say, okay, well, ammonium hydroxide to H2SO4, okay? I can always get one of my ratios from my balanced equation, so it's a 2-to-1 ratio. In other words, twice as much ammonium hydroxide is used compared to the sulfuric acid. Then I look at what I've been given. I've converted this 0.00565 are the number of moles of the ammonium hydroxide. And my unknown is how many moles of the sulfuric acid will I need. Okay, so we cross multiply this, and so you get 2x is equal to 0.00565. Basically, we're just solving this proportion or this ratio, and then divide by 2. And so when I do that, I'll type it into my calculator, 0.00565 divided by 2, and I get 0.002825 moles. So that's the number of moles of the sulfuric acid I am going to need, 0.002825 moles. That's how much I'm going to need to neutralize the ammonium hydroxide. And some of you are going to say, well, Mr. Webster, how come it's not the same amount? How come it's not 0.00565? You think you'd need the same number of moles. But remember, according to our ratio, twice as much, that's what that 2 means, twice as much of the ammonium hydroxide is needed for every mole of the sulfuric acid. So that's what the mole ratio did for us. Okay. But they didn't want the number of moles of sulfuric acid. They want to know the volume of that concentration. So this is where we do step number 4 of stoichiometry, which is to convert back to what's required. Well, we know that the formula is C is equal to N over V. So V is equal to N over C. So here we go. It's going to be 0.002825 moles divided by 0.5 moles per liter. And when I divide those, divided by 0.5, I get 0.00565 liters. Okay. So it just turns out in this particular case that it was you need the same amount, and hopefully you guys can see why. You'll see that there's a certain connection here. The connection here is that essentially you need you need half as many moles. I'm just going to underline this. You need half as many moles, in this case, of the sulfuric acid, because of the mole ratio. You need half as many moles, and so, but in this case, you've doubled the concentration, and so that's why when I have here, if I have 0.00565 milliliter or liters, I apologize. If you have 0.00565 liters of the H2SO4, you will have half as many moles. You'll have half the number of moles. Anyway, don't worry about it like that. You don't need to see that connection. in order to do this question. Basically, you're just going to move through your steps of stoichiometry, and that's going to lead to this final answer, which is 0.00565 liters. So there it is. Like that's a typical question involving acids and bases. You use your steps of stoichiometry, you write your equation, you calculate the number of moles, you use your mole ratio in step 3, and then you convert back to get, in this case, your number of liters of the sulfuric acid. Okay, so basically your homework is going to be to practice some of these. I have to admit that, basically, it's, in a lot of cases, you're just going to have to practice calculating, writing the equation. Like here, look at for number 12. You'd have to do, it says it's hydrochloric acid, which is HCl. And then for A, they're gonna combine it with sodium hydroxide. Okay, and so getting used to writing that neutralization question. Here for a B, it's hydrochloric acid plus ammonia, which is NH3. Now, the one thing I'm going to show you here for when you combine hydrochloric acid with ammonia, whenever you combine it with ammonia, your two products in this case are going to be, it's going to be NH4, NH4Cl, and it also makes water, but you don't need to write the water. If it's a nitrogen one, like this one, a nitrogen base, you only need to write the salt. The water is happening in the background. In this case, for HCl and NaOH, you're going to make NaCl plus H2O. So just be aware, in some cases, you don't have to write the water. Here, we'll do the last one, just so I've started that. It's HCl plus calcium hydroxide. And it makes, it makes calcium chloride plus 2H2O. So there's it'll be a 2 here. There you go. So those are the 3 ones that you would have to do for number 12. Those are the neutralization equations. So that's maybe that's a good one to try, is number 12 there. Here you can see that they've got you writing some neutralization reactions, just some practice writing some neutralization reactions. And then number 4 is very similar to the one that I just did, except in this case, they're asking for the concentration of sulfuric acid. So here, I'll just give you a hand with this one. It says H2SO4 is sulfuric acid, is completely neutralized with an ammonia. So look at this, we would write NH3. And this is one of those ones where you don't need to write the water. Look at this. It's going to make NH4SO4. But again, this is NH4. Because a sulfate is -2, you're going to need to put a 2 here. And then as a result of that 2, you're going to need a 2 here to balance it. Okay, so just be aware that will lead to, that's the balanced chemical equation. And then, so that would be step number 1 of stoichiometry. Look at this, you've got a volume here of 25 milliliters. They're asking you to calculate the concentration of it, but you've been given a volume here of 32.8 milliliters, and they've given you a concentration of 0.116 moles per liter. And so here we go. You're good to go. Now, it does say that water is formed here, but in order to, what I can tell you is, we'll get a lot more into this in the grade 12 chemistry course, is that the water's in the background. You don't need the water to balance the equation. This is essentially as much as you need to balance it. Okay, so you're good to go now. You've done step number 1 of stoichiometry. Now you need to do step 2, convert to moles. Step number 3, do a mole ratio. And then step 4, convert back. And so I think you're ready to go on that one. Okay, good luck with that, you guys. Let me know if you have any questions.